Hi, I'm Margaret from the CBM.
And I'm Cassidy from University of Minnesota Rochester. And what we're going to do today is show you how I use the Serine Protease model set in my classroom on the first day that we use it. So a little bit of background about how I teach in my classroom is that I use these in class. I have a 50-minute class period. Students work in groups. Before they come into my class, they will have watched a content video and answered a few pre-class questions that are related to the content. So they are coming in hopefully knowing a little bit about the serine proteases, have already been asked a few questions, but the first day is just a model exploration activity to get them used to the different models and the renderings, because my students will have seen physical models and virtual models of proteins, but not this many different models and of this many different renderings at the same time. And so usually how I start out every single class period is I talk about the color and the orientation of the models so that everybody's kind of starting out roughly on the same foot. I also ask them if they have any questions about the content from the video, and that kind of gets us like remembering, oh yeah, we're talking about the serine proteases. I may have drawn something on the board to kind of jog their memory. And so when it comes to the models, they will all be kind of laid out on the table like this, because this is model exploration. It's kind of like a puzzle piece activity. So I lay everything out, and the more sort of random you can get things is better. So you don't necessarily want the elastase surface plate right near the elastase binding pocket. So the more you have it spread out, the better. The other things that I use that go with this activity are these what I call CPK colored dot stickers, and then I use these gem stickers. It really doesn't matter what other sticker you use, it's just not the same stickers as these ones. So how I orient students to these models is I first start by saying these are the active sites only of the serine proteases. One is elastase, one is trypsin, one is chymotrypsin. Only the catalytic triad and the binding pocket residues are shown on the backbone, and the residues that are shown are in CPK coloring, and my students know what CPK coloring means. If yours have not been introduced to CPK coloring, you may want to write it on the board so that they have a constant reference. What you'll find is that students will go, blue is nitrogen, and it's just a really long process for them to connect color to atom, and then they have to connect this to a particular amino acid, and even that can take a long time.
Practice with everything. It took me a while to figure them out, but now I'm very comfortable with it.
Right.
And we have to remember the students aren't experts, and it will take them time.
Exactly. And I think that's another thing to consider, is that it takes time to use the models. It is an extra amount of time as far as instructionally, and as far as like the students. Giving them as much time as you can to use the models is really helpful. So if I had a laboratory, a biochem lab to use these in, I might, bring them also into lab and then have longer discussions with them.
Do you think, after you've used this for several semesters now, do the students learn better than they did before they had models?
I think they make connections between the content and the renderings better. So we have some evidence to suggest that yes, they do learn better with the models on certain types of questions. Not, again, on all questions across the board, because, again, it's not like a magical pill that they're taking by using the models, but they are able to answer certain questions better using the models. I have maybe more sophisticated answers as well.
Good. Good. So tell me more about this activity. I'm going to be playing the role of the student. I have a background in molecular genetics, so I don't know serine proteases the way Cassidy does, but
and you've never done this activity.
I've never done this activity, so what are we going to do?
Okay, so I will have introduced them to what the renderings are. So this is the backbone showing only specific side chains and CPK coloring. This is the surface rendering, which is just is if you would show all the atoms here and drape a blanket over it. That would be what you would be seeing with the surface. And again, there's one surface for each enzyme. And then these small molecules are the substrates, and there will be one best substrate for each enzyme. So the first question just asks them to figure out which surface plate goes with which backbone.
Okay, I'm going to think like a student, and I'm going to say, gee, I see purple backbone here, and I see purple backbone there, so I bet this one fits somehow here. And I'm thinking like a student. I looked at where the magnets were, and there I have the surface plate over the top of that protein. I'm going to do the same thing. I see the yellow here, and just an aside here, originally these pieces were removable because you couldn't get the surface in without removing them, and Cassidy found that her students got frustrated trying to fit both of these together. So in this iteration, these pieces are glued in, so it gives them a little bit of a hint as to how to orient them. It's very satisfying to hear that click.
Right. And a lot of students will also use the magnets as a guide, which is fine. There's really no right or wrong way to do this.
And this one doesn't have a piece that comes out, and so it's a little bit tighter fit, but it does fit in there.
Perfect.
Okay.
Okay.
Now, am I done for the day?
Yeah, no, you got question 1 right.
Oh, right. Okay.
Okay. So then the next question asks them to use just observation to determine which set is which enzyme. So which one is chymotrypsin, which one is trypsin, and which one is elastase.
And I didn't do my homework, so
Okay.
I don't know the answers to that.
So I'll give you a few hints. So elastase has the smallest binding pocket because it selects for small, uncharged amino acids. So we'll have a small binding pocket that's mostly hydrophobic.
Okay, and the binding pocket is this hole right here.
Yes.
That's hydrophobic, but it seems pretty big. It takes most of my index finger. This one is fairly flat, but this one seems to be the smallest.
Okay, good. So that one's elastase.
This is elastase. Okay.
So you can set that to the side.
Okay.
And then the next one, we'll talk about trypsin. So trypsin selects for positively charged amino acids, which means it has a negatively charged aspartic acid at the base of its binding pocket.
And negatively charged is going to have oxygen. Oxygen is red. I see some oxygens here. So which one did you say? Elastase?
Trypsin.
Trypsin. Okay. See, I'm not going to remember the names,
That's
but this is, so elastase, trypsin.
Yep.
So by default, this one must be chymotrypsin.
Yes.
And what does
exactly.
chymotrypsin like to bind?
So it binds larger
Big and
aromatic.
nonpolar.
Yep.
Yeah.
So phenylalanines and tryptophans.
And that fits really well, I can see here. Although there's an oxygen there, it's not facing towards the binding pocket.
Yes.
In the binding pocket, I just see a gray carbon.
Perfect. And then, so this is a good place where you can have a discussion with the students. One thing that I like to do is say, okay, so let's talk about that binding pocket size and shape again. And the best way to look at the surface place binding pocket is actually to flip it upside down, because then you can actually see the shape and the size difference between all three. I think the easiest view is to look at it from this direction, so you can see that it really is a pocket or like a cave-like structure.
Oh,
and
and
the
you see
elastase
this
is
is much
very small.
smaller.
Exactly. A lot of students are surprised by how wide the chymotrypsin and trypsin binding pockets are, but that actually makes sense because phenylalanine and arginine are the same width.
So here's an arginine.
Arginine is
Is here.
this one, same width as phenylalanine. So they're
So you can
usually really
see.
surprised by that. But there is a really distinct shape difference between all three of them, and I think the surface plate highlights that really well. And the activity also asks them to comment on, ask them to comment on their observations and how do they know which is which. There we go. And it also asks them to look, and once these are assembled together, ask them to look at the difference between the catalytic site and the binding site. And this is also a point where I like to orient students again. So I will have them place the catalytic triad either all on the left or all on the right, because they should all line up so that the binding pocket is, in this case, just to that side of the catalytic triad, which is to this side. And that way they're all looking at it in the same directionality. And again, we're looking top down.
Okay, so I noticed something here that makes sense. If you're going to be cutting the peptide backbone, which is polar, you should have polar residues in the catalytic triad. And I see lots of red and blue, so that is a good sign that that's the triad.
Right. And what's interesting is that those are there for the ability to create a good nucleophile, not necessarily the ability to bind the substrate. So the binding, the sticky part, what makes it kind of sticky and stick inside is what's in the binding pocket. But these, yes, they do need to be polar in order to have mechanistic properties or acid-base properties. And then the next piece, so they're going to make all their observations and talk and things like that. And what I sometimes have to remind students is that for my students there is a worksheet to fill out. A lot of them will just pick up the pieces and start playing with the puzzle, which again is fine. You can do this however you want because they see that there are many pieces and they assume that some of them are specific to where they go with. So they do a lot of playing around without maybe necessarily following the activity. Again, you kind of do it however you want to. So because we took the color off of the CPK surface plate, we wanted to make sure that they connected, that these two are really similar. So what we'll have them do next, and maybe you can just do one as an example, is to place a blue dot on the surface place where they see blue, and a red dot on the surface place where they see red. So they're kind of constructing a CPK colored surface plate. And this takes them a minute, but there's a group.
You have to have good manual dexterity to
right,
do this.
And you have to pick stickers that aren't too sticky, but they come off easily.
Do you have a brand of stickers that you know works well? Because I just lost my blue sticker.
You know, this one, I don't even know what the brand is. I know I got these at like a Staples, and I just wanted CPK colored stickers that were small, and it just so happened that they weren't overly sticky. So then they make some observations about like what's similar between all the three, what's different between all the three.
Well, the way they're oriented, the blue is always a little bit above the red, but they're close together.
Yep.
And they're always to the right of the, in this orientation, they're all to the right of the binding pocket.
Right, and they all have a catalytic triad that is identical. They all have binding pockets, but the binding pockets are different in both shape and electronics.
And see, my misunderstanding when we first did these was I thought this whole thing was the binding pocket, not the little pocket down here.
Right, so there's vocab here. So the way that I talk about this is the whole thing is the active site. And the active site has two components, a catalytic piece that does the catalysis and the binding piece that does the selectivity. And together those are the active site.
Along with the rest of the shape here.
Exactly. And the nice thing about the serine proteases is that the catalytic site, those residues are distinct from the binding residues. Those are very unique residues and they have different functions.
Which makes it a great teaching tool, which is why it's in every biochemistry textbook. Okay.
And they're on the surface of all the enzymes. They're not buried deep in some pocket that you have to like crack the enzyme open to see and understand. Okay, so the next part is the fun part, or the next most fun part, is to figure out which substrate goes with which enzyme. And
okay, so I didn't do my homework, so maybe you can help me. Can you tell me what is the target of chymotrypsin?
So this one is going to be large aromatic residues.
Okay, so I'm going to guess that maybe something like this.
And why did you pick that one?
Because I see an aromatic ring here.
And why didn't you pick this one?
Well, I hadn't
Or
gotten
this
to that
one.
one.
Or that one.
So I would have put
You
these
grabbed the
two
first
aside.
aromatic you saw.
I grabbed the, so these three are possibilities. And in fact, this one has two different places it might work.
Right.
These two look similar to each other, but wow, they look different too. So these must be enantiomers because I remember hearing about that earlier. So let me just see. Okay, that fits in there, but it's supposed to bind. Where's it supposed to cut?
And then at this point I usually say, just so you know, one of these molecules is an inhibitor. And at a certain
I bet
point,
this is an inhibitor.
right, you play the game, which one's not like the other ones, and set the inhibitor to the side.
So I bet that's the inhibitor and that's the way it fits. Am I right?
Mm-hmm.
Woohoo!
And I also usually tell students, you'll know what fits is when the substrate will make a lot of contact with the surface.
Yeah, so this fits really well in the pocket.
Yep.
But I see, because it's got a sulfur here, there's no way it's going to make that cut.
Exactly. Yep.
So that's an inhibitor for that one. Okay. So these two, well, that fits in the pocket, but it doesn't line up at all with the catalytic site.
Okay.
And this one, that fits really nicely. And wow, I can see right here there's a, don't know if you can see, but here's where the peptide bond would cut. And that fits right between the red and the blue.
Yes.
So I think this is the right molecule to be cut by this enzyme.
You can leave it inside the thing. So what you'll notice is that Margaret's combining her content knowledge with the model. What you'll notice in class is that a lot of times students will not be doing that. They'll just be trying to be like, okay, I don't know. They're kind of doing a guess and check. But then the activity or you as the instructor can bring them back to the content. Okay. So you made a lot of really great connections, which is also because you think more like an expert, I believe.
Even though I'm not an expert in biochemistry, I can
right,
think like
exactly,
this.
yeah, because you're really thinking out loud.
This is chymotrypsin.
That is chymotrypsin.
This is trypsin. Mm-hmm. And what's the rule for trypsin? It looks like it has some kind of a polar binding pocket.
Yep, with negatively charged residue in there, so it will.
And you said this is going to be for arginine. Right?
Positive, so it could be for lysines or arginines.
So I put a lysine in there, and that doesn't fit. Will it fit for either in this? Oh,
it will not. It will only fit best for one of them.
In this model.
In that model, yes.
But so will this enzyme typically cleave either after a lysine or an arginine? Or
yes.
Okay.
As long as there's a C-terminal peptide bond after that, whatever fits in the pocket.
Okay.
In these models, it doesn't. It only will best fit
the one. Right. Okay. So the students could try either one.
Exactly.
Because we know either one could fit because there's a negatively charged red oxygen and a positively charged big residue. Mm-hmm. And when I do this right here, I see, wow, look at that. The peptide bond is right over the top of the catalytic site. Mm-hmm. Okay, so then this is elastase. Mm-hmm. And elastase, by process of elimination, this has to be the one. Yeah. But elastase has a small pocket, and I only see carbons in there, so it must be a nonpolar residue. And it's fairly small.
So as Margaret's fitting this one, that reminds me, another thing that I usually do with the students before we start the activity, or at some point in time, maybe during the activity, is if they're really struggling with the substrates because they have funky shapes and there's lots of colors, I will remind them that these are peptides and that maybe it would be a useful exercise to draw out the peptide sequence on a piece of paper so they can see what the side chains are, how many peptide bonds there are, and even having the students locate the N terminus and the C terminus so they can kind of trace a line from N to C is really helpful for the students who are looking at, typically in class when I draw a peptide, like a tripeptide, it is completely straight across with all the side chains pointing down, and of course in 3 dimensions that's not the reality, and so then the students looking at, in this case as a tetrapeptide, they're not even sure where the side chains are exactly. This one has the distinct arginine guanidinium on it. There's this blue that's sticking out here, but some of them might think that is the N terminus.
Now, did I get this in here correctly?
Yes, that one is in there correctly.
So I was surprised about this one because it's a very shallow pocket, mm-hmm. and there's actually an oxygen atom in the substrate that's really close to the oxygen atom in the catalytic site. Right. But it also lines up where it's supposed to so that your peptide bond is right there.
Exactly.
So I wasn't comfortable with this one because I saw 2 red atoms together, and red repels red because they're both oxygen.
And not necessarily, right? Because one could be an OH and the other could be a carbonyl oxygen and there
Okay.
could be a hydrogen bond.
Great.
So it's not necessarily red and red are a clash.
Okay.
Red and red can actually be stabilizing in some cases.
Okay, see, this is
Yeah.
the biochemist versus the molecular geneticist.
Yes.
Okay.
Yeah, and this one, again, in this model version, the last day substrate is a little bit more satisfying because it does fit nicely, but the alanine methyl group that it selects for is so small that it doesn't really, I mean, there's still a little bit of wiggle room there, which students are like, are you sure that that's right? It doesn't seem like it takes up the space of the binding pocket as well as it should. But that's, again, just another interesting point to have a conversation with your students about.
Now, does this only fit alanine, or does it also fit other things like leucine or?
Leucine and
Valine?
isoleucine and valine are all too large. Sometimes
So
a
this is a
serine could fit.
Really
in
a
there.
small pocket.
Exactly, a very, very
Okay,
small
wow.
pocket. And this one has an isoleucine side chain here, which it's not going to fit in there because of
I
the whole
tried.
shape of this, but it is
I
actually
tried
too
and
big
it wouldn't
to
work,
fit.
yeah. You can go ahead
Okay,
and talk, I'll work
so
on this.
so again, students can get to this point and figure out like which substrate goes with which enzyme. Again, I ask them to make some observations about, well, how did you know that this went in here, and in more vocab than it just fit. What do you mean by fit? Does it fit electronically? Does it fit shape-wise? There's a lot that you can add here. And then in order to have them go and talk more about the content, like layering the content onto the model, like Margaret had already done, I will move into the next pieces, which is where the next set of stickers come in. And what I have them do is I just have them pick one set of enzyme to substrate. And what I want them to do is put one sticker in between the serine and histidine of the catalytic triad, which I'll go ahead and just demo here. And then I have them put one sticker on the peptide bond that should be cut. Again, this is getting them to think about, wait, is it going to cut all the peptide bonds or like a specific peptide bond? But when I take this out, the N terminus is here and the C terminus is here. So it should be the peptide bond to the C terminal side of the amino acid that was selected for. So they would put another sticker. So I want one sticker in between the serine and histidine of the catalytic triad, and one sticker on the peptide bond that's going to be cut. And really, what we're trying to emphasize again is that only one peptide bond will be cut because it's closest to the active site. And when they put the stickers on here, they'll notice that the stickers are touching, or should be touching, because those two functional group, this peptide bond functional group is close enough to the serine so that it can actually become or perform as a nucleophile. And then the last piece is a question about the stereochemistry. So as Margaret had indicated before, she knew that there was a set of, they're actually epimers, they're not true enantiomers, but in the chymotrypsin substrate on the side chain that is selected for, that alpha carbon, the alpha hydrogen, and the alpha side chain have been reversed in position. So if I line these two up in this directionality, maybe I'll put them face down. In one, the side chain is at the bottom, and in the other one, the side chain is on the top. And so the last question asks them about, well, how does that impact the catalysis and or binding of the enzyme to the substrate if the stereochemistry has been switched? And so they have to, again, play with these two pieces to figure out, okay, well, it fits best here, but now the peptide bonds are too far from the catalytic site, and switching the stereochemistry means that it'll be too far away from the catalytic site, so it still binds. So binding is relatively unaffected, but catalysis is greatly affected.
That's cool.
Isn't that crazy?
Yeah.
Yeah. And then, again, this is the inhibitor, and the sequence in which I teach enzymes is I start with binding, and then I go to transition state stabilization, catalysis, Michaelis-Menten kinetics, and then I use the serine proteases to kind of pull all of those things together. And then the final day is inhibition, so I will bring these back and we'll talk about inhibitors. This is a competitive inhibitor for chymotrypsin because it has that phenyl group on it, and it will kind of fit here, but not that well. So even if this molecule happened to run into this enzyme, it won't stick long enough to have any effect on inhibition. And again, there's no way that
That's
it's
just
going
way
to
too
fit.
big, yeah.
Exactly. So that is the inhibitor. Other things interesting things that I've noticed is, again, the more time you can give the students, the better questions they tend to ask. But they do say some really odd things. They do sometimes talk about the surface plate and the enzyme as separate molecules, or they think the surface plate is the substrate. So there's some vocab, interesting things with vocab that go on with this. And when the models bring out really great discussions, like in class and within groups, but when they have to move to the activity to write about their observations, something is lost in communication. They're not really quite sure how to write about what they see and touch, and
So it's a conceptual understanding they can demonstrate, but they can't necessarily put words in.
exactly. They'd rather just talk with me and their peers about the models than have to write about it on a piece of paper. The other thing that I noticed in my classroom is the last time that I did this, they're all in groups and I'm kind of just wandering through the room. I field questions, or I might, ask them questions or poke them in a certain direction. But one thing I noticed, as I'm looking around the room and we're set up in a circle, I looked around the room, and for every single group, only the male members of the group were holding the models. Most of, all of the female students had their hands underneath the table or just sitting, kind of just keeping their hands close to them. And we kind of had to have like a moment where I was like, okay, stop, hold on. If you're holding the model, pass it to the person to your left or to your right, because it was definitely a female, because I have way more females in my students than in my classes than I do males. And we talked a little bit about gender differences with spatial reasoning and why we're using the models, and don't be afraid to hold the models and touch them and try and figure out like what is really going on here. And so I guess that's just another thing that I usually end up bringing up with my class at some point is like, why are we even using these models? Like, why do we bother? Why are we bringing
If you're afraid
this
to
out?
touch them.
If you're afraid to touch them, or, they're not toys, they're not gimmicks. They're designed for a reason, and they may not help all of you equally, but they may help some of you. And one way to learn is just to pick something up and to see how it feels and to touch it and to interact with the model. So you may have to have a conversation about like, why are we using the models? What's the point?
They're just cool. We hope you'll try these in the lending library. Please give us feedback so we can continue to design and build even better models.
The activities are also available through the Milwaukee School of Engineering CBM website. And there is a follow-up activity that I do with my students that comes the next day where they don't necessarily have to use the models, but again, it's about serine proteases, so that will also be available.